Okay, so to continue with our discussion, so we now proceed with the integral of transcendental functions. So these are functions which are not algebraic. So what we tackled last meeting was the basic formulas, which was all about algebraic formulas. So um, they were just simple formulas pertaining to algebraic properties. So what are transcendental functions? So of course, these are functions that are not algebraic, and we have four different types of transcendental functions. So what we need to tackle is the first part, or the first half of the trigonometric integrals, because there are two topics for this function. And then we also have the inverse trigonometric, your hyperbolic, and your exponential functions. Okay, so if you check your canvas, so I already uploaded the first problem set, which was all about the basic integrals and the trigonometric integral. So that particular problem set is 25 problems. So the deadline for which is on next Friday. Okay, so to start is these are the different formulas for your trigonometric integrals. So you may be familiar with some because most of these are just the reverse formulas for your derivatives. So to check the familiar formulas coming from your derivatives is we have the first two formulas. So if you can observe that the integral of sine u is negative cosine u, because if we try to eliminate the negative sign first, so the integral of cosine is negative. I mean, it's sine, di ba? Pero murag ko lang siya, kailangan siya negative because sa atong derivative, di ba? So if we derive cosine u, so that will be negative sine, di ba? Negative sine u. So that's why it's negative times negative sine u, so that's sine u. So that's why it has a negative here. So the derivative of sine is cosine, so it's correct. So the other familiar formulas is the formulas 7 to 10. So we have also these one from your derivatives. So again, it's just the reverse of the other for the positive counterpart of the functions. So again, if you try to observe the derivative, so they are the same. But in the case for the cotangent and cosecant, so in your derivatives, if we derive cotangent, it will become negative cosecant squared. If we derive cosecant, it's going to be negative cosecant u cotangent u. So in this process, since we are integrating positive cosecant squared and positive cosecant u cotangent u, so that's why we have a negative value for its counterpart. So bali-bali ra siya. So it's just the reverse of the other. Okay, so they are familiar formulas coming from your calculus 1. Now for formulas 3 to 6, so these are your new formulas coming from the integrals. So if you try to observe the value of the indefinite integral for formulas 3 and 4, 3 to 6, so these are ln, meaning there are logarithms, natural logarithms. So if we try to derive these natural logarithms, so we still need to use the process of the derivative for natural logarithms, which is du over u. So there's no direct formula for these four formulas. Okay, so if you want to memorize these four, so you can memorize it, but you may also not memorize it since you'll be able to integrate it using u sub, since the answer is ln of cosine u plus c, ln of sine u plus c, so on and so forth. So what you need to achieve here is, in a given integral, you have to achieve the form of integral of du over u. So let's say you forgot the formula for tangent, cotangent, secant u, and cosecant u. So you may solve it using by transforming your given integrand into its corresponding du over u format. So you need to use the u sub technique. Okay, so for us to appreciate the different formulas for trigonometric integrals, so we have to solve these 8 problems. Okay, so from the basic formula going towards the most difficult problem. Okay, so let's begin with the basic formula. So you might as well know that cotangent x dx is already a given formula. Now let's say you forgot or you forget how to, you forget the formula for this particular function. So again, there's another way to solve this one, and that's by using u sub. So how do you use u sub? So again, the answer for this one is ln something, if you recall in the previous slides. So if we try to break cotangent even further, so you have cosine x all over sine x dx. Okay. So next is we need to determine our u sub. Okay, so u sub is, again, since the pair of your dx is multiplied with the numerator cosine x, so we'll be expecting that the value of your du is cosine x sine x. Or it may be the partner of dx is dx over sine x, so it's still possible that the partner of your dx is sine x also. But in this case, so let's try pairing up dx in the numerator first. So let's say this will be our du. So trial and error method na siya. Let's say this one is our u parameter. Okay, so u is equal to sine x. And again, taking the derivative of your sine x, so that's du is equal to cosine x times 1, because the derivative of x is 1, then dx. Okay, so if you observe again the given equation, so it's safe for us to say that we have given the right assumption. So this will be our du, and this will be our u parameter. So every term in the equation has been replaced by the u parameter. Okay, so changing the whole equation, so you have du over u for our final form of the formula. And again, this one is a basic formula. So you have ln of u plus c. So to give the correct answer, so we need to bring back the value of your u parameter in the equation. So that's ln sine x plus c. So that's how you get the answer. Okay, so questions so far or clarifications? Okay, so let's proceed with the next example. So in example number 2 is we have cosine 5x. So again, since we know the formula for cosine, so the integral of cosine is just sine. So let's say we can just answer this one immediately. Sine 5x plus c. So you might say that this one is the correct answer. But if you try to prove it by deriving the final answer, so let's derive sine 5x plus c. Okay, so the answer of which is the derivative of sine is cosine. So cosine 5x. Then we need to derive 5x times 5 plus 0. So the final answer is 5 cosine 5x. So if you notice that the given derivative is not the same as the given equation, it's only cosine 5x. Alright, so meaning our answer earlier is not correct. What so what is lacking in our equation? So again, if we try to go back to the formula, so the formula states that the integral of cosine x is equivalent to sine x plus c or u, depending on the variable you want to represent your angle. So take note that in the given equation, in the cosine x is equal to sine x plus c, the coefficient of the angle is only 1 here. It's 1. So what about if we have a multiplier or a coefficient in our angle? So if you try to research mathematical books, especially in BS Mathematics, so the real formula for the integrals for the trig functions is this one. So cosine, so a of x, so meaning a is the coefficient of the angle. So the answer for your corresponding integral is 1 over a sine ax plus c. So this is the original equation. Okay, so we have coefficients in our angle. So in most books, what they present in the book is just this one, because of course most of the angles presented or the problems presented in the books are just simple, so without coefficients in the angle. But in most problems or advanced problems, so we have to deal with coefficients in the angle. So that's why this one is also important to know. Okay, so this one is also applicable to the other trigonometric integrals: sine, integral of sine, integral of tangent, integral of secant squared. So as long as this one is present, the angle is present, so you need to generate 1 over a in the final answer. So trying out the formula, so again, since 5 is the coefficient, so we can say that the answer is 1 over 5, then sine 5x plus c. Okay, so with this, we can say that by differentiating your or by verifying your final answer, so that's 1/5 sine of 5x plus c. So that's 1/5. Then cosine 5x. So again, take the derivative of 5x times 5 plus 0. So eliminate 5 or cancel out 5. So what remains in your derivative is cosine 5x. So now this one is now equivalent with the given equation. So it means that our answer is now correct. Okay. So again, what happened here is that since we have a coefficient in the angle, so we need to, so see, again, since we have a coefficient in the angle, so we need to generate a particular term for it to be cancelled out in the process of differentiation. So that's why we have 1 over a in its particular value of indefinite integral. Okay, so do you have questions? Okay, so let's proceed with the next. Okay, so so we have the integral of sine x minus cosine x all over sine x dx. So if you try to look at the formula, so we cannot still use the different trig formulas presented to us. So we still need to break it down even further. So we can have two different integrals. So this one will be the first one, and then the other one is the second integral. So we're going to have two terms. So this will be 1 minus cosine x all over sine x dx. So distributing, okay, distributing is that we have integral of dx and then minus the integral of cosine x all over sine x dx. Okay. So furthermore, so we have dx, then minus this one is cotangent x dx. So the final answer is, so again, if you don't know the integral of cotangent, so try going back to example number 1. So minus ln of sine x plus c. So that's your final answer. Okay, so questions? Okay, so simple pa no? Simple. So problems are still simple. Okay, so let's proceed with the next example. So this one is, it may be a bit complicated for us to solve now. Okay, so upon observation is we have an algebraic term in the numerator, z plus 2, and then a trig function in the denominator, cotangent of z squared plus 4z minus 3. So what you need to do here, again, so I'll still guide you in the process. So what we need to do here is we need to use u substitution. So u substitution. So again, to give you tips on the u sub is that you need to replace first So replace the complicated term. So in the previous session, our complicated term is the higher degree equation. So we let the higher degree be the complicated term because again, if we have underwent through analytic geometry, so it's easy for us to graph the linear equations compared with the quadratic equations, di ba? So that's why our z squared is much more complicated compared with the linear equation. Okay, so the first step is to replace the complicated term. So next is you need to derive, and then upon derivation, so the derivative must be present in the equation. The derivative must be present in the equation. So those are the three tips or processes that you need to undergo in the use sub technique or in the sub technique. So here is if we try to follow the process, so replace the complicated term. So in the given equation, so of course the complicated term is not your cotangent since again if we try to look back in our given integral formulas, so we have an integral for cotangent. Okay, now the complicated term here is z squared plus 4z minus 3 because we want that our final form of the equation will be in terms of cotangent u na lang. So let's try to use another. Okay, so u is equal to z squared plus 4z minus 3. And then du, so if we try to get the derivative, so derivative is 2z plus 4 dz. So if we try to observe, so again after deriving, so the derivative, so check na siya, check. So again in the third process, the derivative must be present in the equation. So looking at the derivative, that's 2z plus 4. And then looking in the equation, we have z plus 2 dz. So this particular term here in the numerator. So meaning our derivative is partially correct. So we need to make some adjustments for us to replicate the given term in the integrand. So we need to factor out 2 here. So you have 2 z plus 2 dz. And then divide 2 to the other side for us to fully replicate the term in the numerator. So du all over 2 is equal to z plus 2 dz. Okay, so you can now replace every term in the equation. So this one is your u parameter. And then the numerator will be du all over 2. So we can now solve the equation. So you have the integral of du over 2 all over cotangent u. Okay, so taking 1/2 outside the equation because 1/2 divided by 1 is still 1/2. So this will be our constant of integration. And then 1 over cotangent. So 1 all over cotangent is tangent, diba? That's tangent u du. Okay? So again, if you don't know the formula, so we can solve it for even further. So again, breaking down your tangent, that's sine u all over cosine u du. Then again, using again u sub. Now since we are already using the u parameter, so you can use another technique or you can use another variable. So let's try. So again, always determine the complicated term. So here, murag walay complicated, di ba? So either could be one or the other. But always take note of the third process. So the derivative must be present in the equation. So if you try to derive sine u, so the resulting answer will be cosine u du, di ba? So notice that du over cosine is not possible because it will be a fraction. Yeah, this one is a product. So here our derivative here is the derivative of sine u is negative sine u because the derivative of cosine is negative sine. So negative sine u du. So we can replace it since the numerator is sine u du. Okay. So more likely your sub technique is more of a trial and error process because we don't know what really is the outcome of your um, solution or what you have declared in your sub technique. So that's why you need to practice a lot of problems for you to be able to understand or or get the process of um, getting the fastest way in the U sub. Okay, so here is we let u be cosine. So instead of u, so let's try using another variable because again we are now using u variable. Okay, so let's try using a. Let's say a. So let a be cosine u. So it's still the same as the sub technique, but again we are just using the variable a since we have the u parameter present already. So taking the derivative of cosine, so dA is equal to negative sine u du. So again, the derivative must be present in the equation. So the numerator is sine u du, and we have negative sine u du. So dividing everything by negative 1, so we have sine u du. So this will be negative dA. And of course, your denominator will be the a parameter. Okay, so integrating or replacing. So 1/2 the integral of negative dA all over a. So you have negative 1/2 integral of dA all over a. So that will be negative 1/2 ln of a plus c. So replace your a parameter, that's negative 1/2 ln of cosine u plus c. And then replace even further the value of your u. So let's write it in the lower left. Okay, there's no space. So our final answer is negative 1/2 ln of cosine z squared plus 4z plus minus 3. So this one is minus 3 plus c. So this one is our final answer. Okay, so notice that we underwent two sub-technique process. So the first one is the U sub, because that's the process is all about. So next is we replace it by A again since we already have the U sub. So let's call it the A sub in the next sub-technique process. So that will depend on how many times you're going to use the sub-technique in your solution. Okay, so questions or clarifications? Okay, so I hope you understood the process in this example. Okay, so let's go to the next example. So this still the same concept as the previous example. So notice that your equation is a bit complicated. So you have a trig function, a logarithmic function, and then an algebraic function in the denominator, which is x. So again, we need to use u sub. So again, another purpose of u sub is for us to eliminate or for us to replace the complicated term with a simpler term. So that's why it becomes u. And we have to deal with the u parameter only instead of the complicated parameter. So here in so in this example, so the complicated term here is this one, the ln 4x squared. So automatically this one becomes your u parameter. So you have ln 4x squared. Okay, so to get its derivative, so du. So again, the derivative of ln. So again, if you forgot the derivative of ln, so let's write it on the right side. So the derivative of ln, so derivative of ln of ln u is equivalent to du all over u. So again, it's important for us to learn the derivatives also because in the process of the sub-technique, you'll be needing to derive your equations also. Okay, so du, so meaning that's the derivative of the angle. I mean, of the base of your natural logarithm. Okay, so the derivative of 4x squared, so that will be 4 times 2x to the power of 1. Then all over u. So meaning you have to copy again the value of your value of the natural logarithm. So that's 4x squared. So cancel 4, cancel 4, cancel 1x. So what remains in the answer? So dapat na dx dito. So what happens in your final form is you have 2 dx or 2 over x dx. So again, after getting the derivative, so we need to look at the equation if that particular derivative is present in the equation. So if you can see, dx over x is present, but we have we have the value of 2 in our derivative. So we need to isolate this one for us to achieve dx over x. So dividing everything by 2, so you have du all over 2 is equivalent to dx all over x. So meaning this one becomes our u parameter. This one becomes our du all over 2. Okay? So if you're concerned on how I get the value of the derivative, so again, go back to your derivatives. So that's how I got the value of your derivative of ln of 4x squared. Okay, so next is we go to its substitution part. So the formula now becomes integral of cosine u, and then dx over x is now du over 2. So notice how the equation becomes much simpler compared with the given equation. So taking the constant outside, that's 1/2. So integral of cosine u du. Okay. So again, since this one is a basic formula, integral of cosine is just sine u plus c. So we have 1/2 sine u plus c. So again, don't forget to bring back the value of your u parameter for you to get the full credit. So that's 1/2 sine ln of 4x squared plus c. So this one is your final answer. Okay, so do you have questions regarding this problem? Okay, so mga bright students, okay, wala pa yung concern. Sige. Okay, so let's proceed with the next example. Okay, so in this example, as we have cosine squared 1/2 of x dx, and then if you try to expand it further, so we have cosine 1/2 of x, then cosine 1/2 of x dx. So again, this one is still the same as the original equation. So we have just expanded the cosine squared. Now if we try to use the u-sub technique, so since both are cosine, so if you pick either of the one, so it will result in the same derivative. So let's say we try to obtain the derivative of cosine 1/2 of x, and then we get the derivative. So again, this one is using the u-sub technique. So again, it's more of a trial and error method. So we have negative sine 1/2 of x times 1/2 dx. So the resulting derivative is negative 1/2 sine of 1/2 of x dx. So notice that in the given derivative, so it's not present in your given equation. There's no negative 1/2 sine 1/2 of x dx. Diba? So meaning we cannot use the u-sub technique in this particular problem. So what we need to do is we go back to our trig subject, trigonometry subject, and we learn how to transform equations by using the different identities. La, kuyawan na. So again, we need to use the different identities. So we go back to trigonometric identities. So the purpose of trigonometric identities is for us to be able to replace complicated terms to much more simpler terms. So that's the purpose of your different identities. So it's a way of simplifying further your equations. So trigonometric identities. So if you have memorized or if you have so if you can recall some of the identities, so we have the half angle identities, we have the sum to product, we have the product to sum, we have the Pythagorean identities. So there are a lot more. So we have the double angle, the triple angle. So those are the different trigonometric identities. So in here is for us to save some time. So we're going to use the half angle formula or half angle identity. Okay. So for cosine, so if you try to look up this one, look it up in the internet later on or in your reference later on. So the half angle of cosine is, so let's try to use another. So cosine theta over 2, meaning that's half angle of cosine, is equivalent to plus minus square root of 1 plus cosine theta all over 2. So again, the purpose of your different identities is for you to be able to achieve a simpler form of the formula, or I mean, a form of your equation. So again, since this one is squared, so we square everything, squaring everything. So you have cosine squared theta over 2 is equivalent to, so again, plus squared minus squared is positive 1. Then the square of your square root is, so you can cancel out the square root. So what remains on the right side is 1 plus cosine theta all over 2. Okay, so this will be our transformation. Okay, so to further um, give details in this particular identity, so we have to declare the half angle first before transforming. So half angle becomes a whole angle. So our half angle in the given equation is 1/2 of x. So that's x all over 2. So meaning if we want to get the theta for later, so theta is just equal to x. Okay, so everything's done with the replacement. So we can now change the complicated formula to its new counterpart. So again, another purpose of your different formulas for your identities is the counterpart of which is still equivalent to the original. Okay, so this one is still equivalent to this form. Okay, or vice versa. So we have the integral of 1 plus cosine theta. So again, our theta is x. all over 2 dx. So again, the purpose of which why I am declaring this one is because later on, so in the next example, so you can appreciate why I did this part in the solution. Okay, so breaking it down even further, so you have 1/2, so we can get two terms out of this. So cosine x all over 2 dx. So we have 1/2 integral of dx plus 1/2 integral of cosine x dx. So we have x all over 2 plus 1/2. So integral of sine is, integral of cosine is sine x plus c. So final answer is x all over 2 plus sine x over 2 plus c. Or if you want to combine them, so you can combine them as well. So x plus sine x all over 2 plus c. So either of the three answers are correct. Okay, so questions for this problem? Okay, so next. So this time is we're going to use another half angle. So this one is the sine function this time. So again, half angle. So for sine function or for sine half angle, so that's sine theta over 2 is equal to plus minus 1 minus cosine theta. So earlier that's 1 plus cosine theta for cosine half angle. So for sine half angle, that's minus. So again, to achieve the squared function in a given equation, so we need to square everything. So you have sine squared theta over 2 is equivalent to 1 minus cosine theta all over 2. So again, the squared function is only applicable to the whole function of sine, not to each of the parts of the sine function. So you might think that it should be sine squared theta squared over 4, but that's not correct because theta over 2 is the angle of your sine function. And again, you you square the function, not the different parts of the function. Okay, so next is again we need to declare first the half angle, or we need to identify your half angle. So half angle, so this one is the half angle going towards a whole angle. So our half angle in the given equation, so looking at the format sine squared theta over 2, so our theta over 2 is 3x. 3x. So isolating theta to so that it becomes a whole angle, so that's 6x. Okay, so simplifying the equation is we have 1/2 minus cosine 6x all over 2 dx. So again, if we try to create two terms out of this, this will become 1/2 minus cosine 6x all over 2 dx. So isolating even further, so we have 1/2 integral of dx minus 1/2 integral of cosine 6 of x dx. So we have 1/2 of x minus 1/2. So again, if you have a angle, a coefficient of the angle, so we need to get the 1 over a. So that's times 1/6 of cosine of 6 of x plus c. So the final answer is x all over 2 minus 1 over 12 cosine 6x ups murag sayop. So there's a mistake. So this one instead of cosine, since we already got the integral, so that will be the integral of cosine is positive sine. So this one is sine 6x plus c. Or if you want to put the sine in the numerator, so pidirasad sine 6x all over 12 plus c. So this one is the final answer, or the one above. So that's still the same.
Okay, so questions?
Okay, so just try to review this one later once I upload the recording. And also, um, so have you checked the first upload in the canvas? So try checking it out for you to be able to start with your problem set. Okay, so we have the final example. Okay, so the integral of sine 3x cosine 5x dx. So you might wonder why we have two different angles. So of course, that's the problem itself. So again, if you try u sub, so let's say you let u be 3x, u as, sorry, so that will be sine 3x. So we let u be sine 3x. So the derivative is cosine 3x times 3. So that will be 3 cosine 3x dx. So again, if you notice, if we try to observe the derivative in the given equation, there's a cosine, but it's cosine 5x. So unfortunately, we cannot use again u sub because we need 5 as the angle. But here, if we try to derive sine 3x, the corresponding answer is cosine 3x. So the angle is not the same as the other cosine. So, so even if you try to let cosine be the u parameter, so what will happen is the derivative is 5 cosine 5 negative 5 sine of 5x dx. So again, we have a sine function, but the angle is 3. Here in our derivative, it's sine 5x. So again, we cannot use the u sub technique. So of course, if we cannot use any other technique, so we need to consult with our trigonometric identities. So in this case is we're going to get the help of the particular identity of product to sum. So product to sum. So actually there are two different identities. So product to sum. So I'm going to show you the first solution. Then the other one is sum to product. So there are formulas that pertains to these types of identities. Okay, so let's try to use product to sum first. So Kamudia, if you're listening, so try to use your phone, your free phone if you're using a laptop. So I guess your phone is free. So try searching product identities and verify if what I'm going to write is correct. Okay, so for sine cosine function for product to sum, so that will be sine A, cosine B is equivalent to 1/2 of sine A plus B, then minus, that's plus sine A minus B. So that's the given equation. So notice that the format of the formula is already the same as the given equation. So sine A cosine B. So meaning the angles A and B are different from one another. So it's a unique angle for each function. Okay, so if we try to use this particular identity, so we have to learn first what the values of A and B is. So A is, of course, that's gonna be 3x. And then the B parameter is your 5x. Okay, so sine A, sine 3x, cosine B, cosine 5x. Okay. So next is we have your A plus B term, A plus B. So that will be 3x plus 5x, that will be 8x. Then next is your A minus B. So that will be 3x minus 5x, that's negative 2x. So we can now replace the equation. So from sine 3x cosine 5x dx, so this one becomes 1/2 of sine 8x plus sine negative 2x dx. Okay, so looking at the second term, we have a negative angle for sine. So we have another identity for that one, and that's negative angle identities. So it states that, so negative angle. So negative angle identities. So try looking it up later or now. So it states that if you have a negative angle, so sine negative theta, so the answer is negative sine theta. So it means that we can simplify this one so that we won't be dealing with negative angles. So taking 1/2 outside the equation, so that will be 1/2 the integral of sine 8x. So again, taking the negative outside, so that's sine 2x dx. Okay, so getting two terms or getting two integrals. So you have 1/2 the integral of sine 8x minus the integral of sine 2x. We have dx here. dx. So getting the integral of the first term. So 1/2. So distribute 1/2 to the first term. Distribute 1/2 to the second term also upon integration. So that's 1/2. So again, since we have a coefficient of the sine function, so that will be 1/8. So integral of cosine is negative cosine 8 of x. So minus, so again 1/2, then times, again since we have a coefficient of 2 in the angle, so 1/2 negative cosine 2x plus c. So getting the final answer is we have, so 1/2 times 1/8 times the negative sign, that's negative 1/16 cosine 8 of x. So minus 1/2 times 1/2 times negative 1, that will be plus 1/4 cosine 2x plus c. So this one is our final answer. So this will be for the product to sum identity, or the product identity itself. Okay, so questions? So it's a lot more complicated now since we are dealing with the some topics that is covering trigonometry subject. Okay, so if you don't have any questions, so let's try to solve it again using the other identity, which is the sum to product. Okay, so now we have to solve it using sum to product. Okay, so for the formula for the sum to product, or for the sum identity, is we have sine A. Oops, let's use another color. Okay, so for the sum to product, or for the sum identity, so we have sine A plus sine B is equivalent to 2 sine, so sine of A plus B all over 2, and then cosine A minus B all over 2. So notice that on the left side it's sum, and in the given equation it's product. So the product in this particular identity is on the right side, so that's what we need to follow in replacing our equations. So we need this one for it to be transformed on this left side, because this one is what is replicating in our given equation. So the same earlier. Okay, so since there's still 2 in the coefficient, so dividing everything by 2, so this will become 1/2 of sine A plus sine B, equivalent to sine A plus B over 2, and then cosine A minus B over 2. So what we need to do here is, again, for us to be able to determine the different angles. So determine first the A plus B. So sine A plus B, so this one is sine A plus B over 2. So our A plus B all over 2 is equivalent to 3x. So next is cosine 5x. So this one is cosine 5x. So a minus b over 2 is equal to 5x. So multiplying it to the other side, multiplying 2 to the other side is we have a plus b is equal to 6x, and then a minus b is equal to 10x. So we need to solve a and b parameters because we need these values here on the left side. Okay, so if you have mastered your algebra, so solving two equations, two unknowns by elimination. So by elimination, by substitution, so we have learned that one in your algebra. So canceling out b, so you have 2a is equal to 16x. So your a parameter is 8x, and your b parameter, if we use one of the equations, that will be negative 2x. Okay, so once we learned the different values for your a and b, okay, so we can now replace the equation. So the integral of 1/2 of sine, so sine a is, so let's use the bracket lang first. Let's try to make it clean. Okay, so sine 8 of x plus sine negative 2x dx. Okay. Um, let's find some space. Okay, so the integral of, so we can take 1/2 outside the integral symbol. So that will be the integral of sine 8x. So again, negative angle identity. So taking negative outside the equation, so that's negative sine 2x dx. So integrating further, so we have integral of sine 8x, integral of sine 2x dx. So we have dx also here. Okay, so again, distribute 1/2 once you have integrated your equations. So the first one is 1/2. So again, that's 1/8 minus cosine 8 of x. So that's negative cosine because that's the integral of your sine function. So minus 1/2 again, multiplied 1/2 to the integral. And then that's 1 over 2 negative cosine 2x plus c. So simplifying your answer, that's negative 1 over 16 cosine 8 of x. So negative 1/2 times 1/2 times negative, that will be positive 1/4 cosine 2x plus c. So this one is the same answer as what we have done earlier, the product to sum solution. So this one is the sum to product solution. So that's why they say in mathematics that there are many ways to kill a cat because you can approach the problem in different methods. Okay, so questions or clarifications for this problem? Okay, so I think there's none. So again, you may start answering your first problem set, and it's found under the assignment tab under problem sets. So the deadline for which is next Friday. So since we have tackled basic and trigonometric integrals up until this day, so of course your asynchronous activity towards is for next week. So you have 1 week to accomplish your 25 problems. So have you seen the video the lecture recordings? Ah, sige. So naharada eh. Okay, so I forgot one slide. So if you're going to review all the different identities, so muna siya. So these are the different identities. So what we used earlier is this one, the product to sum, or it's just called the product identities. And what we use in the negative angle is this one. And then for the sum to product is this one. And then for the half angles is this one. So again, there are a lot of different identities to be mentioned, but you only need those that are important. So for next meeting is we're going to um, deal with special cases of your trigonometric functions, which is your Pythagorean identities.